Okay, so let's do some examples where we are predicting molecular geometry using the VSEPR method for some different molecules. So some of these we've drawn the Lewis structures of before, but that's the first step for all of these. So the first step for all of these is to draw the correct Lewis structure. From the Lewis structure, we can determine the steric number. From the steric number, we can determine the molecular geometry. And then the electron pair geometry. And then from that, we can determine the molecular geometry based on how many of the regions of electrons around the central atom are bonded and how many regions are lone pairs. Again, you are going to be responsible for knowing the names of the electron pair geometries and the molecular geometries of steric numbers 2, 3, and 4. There are higher steric numbers, and that is for molecules that do not obey the octet rule. They have expanded octets, and more information would be provided on those examples. I would not expect you to have those memorized. Okay, so let's start with carbon tetrachloride. First thing is we need to understand that this is a covalent molecule between carbon and chlorine because these are both nonmetals, and we need to know how to write the formula correctly, because if we write the formula incorrectly, we'll get the wrong Lewis structure and all of this will be wrong. So carbon, tetra means 4, Cl4. So the way I'm going to write this Lewis structure is I'm going to put the atom with the highest bonding capacity in the middle, which is carbon. And then I'm going to put the chlorines around. So the total valence electrons for carbon tetrachloride, we actually did this one back in chapter 4. So the carbon has 4. I'm just going to write it over here. Carbon has 4. Chlorine has 7 times 4 is 28. So I have 32 total valence electrons. So far I've used 2, 4, 6, 8. So I'm going to distribute the rest of these around to use up the remaining electrons. And 32 electrons will get me so that everybody has a full octet. So this is the correct Lewis structure of carbon tetrachloride. Now we need to assign the steric number. So remember, the steric number is just the number of regions around this central atom. 1, 2, 3, 4. There's 4 single bonds around this central atom. The steric number is 4. So remember, the electron pair geometry only comes from the steric number. Everything that has a steric number of 4 has an electron pair geometry of tetrahedral. So now when we look at the molecular geometry, we have to see how many of these regions of electrons are bonds and how many of these regions of electrons are lone pairs. So if we look at the chart, it tells us if we have something that has a steric number of 4, has 4 bonded atoms and 0 lone pairs, it is tetrahedral. So that means the molecular geometry is also tetrahedral. So there are pictures in your book for you to see what a tetrahedral molecule looks like. And this is not an art class. You're not being graded on artistic ability and how these look. But the way that you represent a tetrahedral molecule is that you have this in the middle again, and you do not show the electrons when you are drawing the molecule in 3 dimensions. You draw a wedge to indicate the molecule that is going into the plane, and then you draw a dash for the molecule that is coming towards you. So the bond angles, I'm not going to ask you specifically about the bond angles, but you should be comfortable identifying and drawing the shapes of molecules for steric numbers 2, 3, and 4. So that's carbon tetrachloride. So let's move on to nitrogen trihydride. So nitrogen trihydride, what this is ammonia, NH3. We also did this one in chapter 4. Nitrogen has 5 valence electrons, hydrogen has 1 times 3, 8 total valence electrons. So when I drew this, I say nitrogen is in the middle because it has the highest bonding capacity. I'm going to put the 3 hydrogens around it. I've used 2, 4, 6 electrons for those bonds. Hydrogens all have full outer shells, so I'm going to come back and put those 2 more electrons on the central atom. Now this is the correct Lewis structure. So from the Lewis structure now I can determine the steric number. Remember, the steric number is just the regions of electrons around this central atom. 1, 2, 3, 4. There are 4 regions of electrons. It does not care if that region is a lone pair or if that region is a bond. The electron pair geometry also does not care. It's got 4 regions of electrons. It's tetrahedral. The molecular geometry does care. It does differentiate between a region that is a bond and a region that is a lone pair. So what we have here, steric number 4, its electron pair geometry is tetrahedral. It has 3 bonded atoms and it has 1 lone pair of electrons. This is called trigonal pyramidal. And the way that we draw this is I'll write that down here. Trigonal pyramidal, or trigonal pyramidal, depending on how you pronounce it. But it would look like this, where here's the nitrogen, and then it kind of looks like a pyramid, where like these are the 3, these would be like the 3 legs of the pyramid. And then we would have the lone pair of electrons here on the central atom. It is not wrong for you to show the electrons in the molecular geometry. It's just not needed. You might see some examples of different work from different sources where it shows electrons and then some where it does not. It is necessary to have electrons in a Lewis structure. It is not in the molecular geometry. All right, let's move on to carbon dioxide. Carbon dioxide is also an example of a structure that we did in the last chapter. So CO2, carbon dioxide, CO2. Carbon has 4 valence electrons. Oxygen has 6 valence electrons times 2 is 12. 4 plus 12 is 16. I have 16 electrons to distribute. We found out that 16 electrons was not enough to satisfy all the octets with single bonds, so we had to come back and do double bonds. So this was the correct Lewis structure for carbon dioxide. So now let's see what is the molecular geometry, the steric number, electron pair geometry, and molecular geometry. The steric number here is 2. This double bond counts as 1 region. This double bond counts as 1 region. So the steric number here is 1, 2. The electron pair geometry only cares about the steric number. If you have a molecule with steric number 2, its electron pair geometry is linear. Its molecular geometry is also linear. So the Lewis structure here is going to look the same as the molecular geometry, except you could or could not show the electrons. So thing to pay attention to here is that a double bond is 1 region, just like a single bond is 1 region. This is not 4 regions of electrons, even though it's 4 bonds. It's 2 regions of electrons. So now let's do oxygen. So remember, oxygen is one of the 7 diatomic molecules. So oxygen is O2. So oxygen has 6 valence electrons times 2 is 12. So I'm going to need a double bond here. 2, 4, 6, 8, 10. Whoops. 2, 4, sorry. 2, 4, 10, 12. So this shouldn't be here, right here. So there is my Lewis structure. This is kind of tricky because there isn't really a central atom to go off any of this. But because there's two and they're the same, there's not really a good, there's not really a good answer for the steric number. But this is a linear molecule. So there really wouldn't be a good answer for electron pair geometry or molecular geometry. But we're going to come back to this as an example a little bit later. It is linear. But by the way that we have defined it, having a central atom, we don't have a central atom to move on. But we're going to come back to this example a little later. Okay, the next one, let's look at something called arsenic trifluoride. So arsenic is AS on the periodic table. Trifluoride means F3. So arsenic trifluoride, arsenic is in group 5. Fluoride is in group 7. And I have 3 of them, 21. So I have 26 electrons to distribute. So I'm going to start on the outside and distribute the rest. And I have just enough to complete all of the octets. So this is the correct Lewis structure for arsenic trifluoride. The steric number here is 4. 1, 2, 3, 4 regions of electrons around that central atom. The electron pair geometry is tetrahedral because we only care about the regions of electrons for the electron pair geometry. For the molecular geometry, if you have 3 bonded atoms and 1 lone pair, this again is called trigonal pyramidal. So we would draw it like this. Again, no need to show the electrons in the molecular geometry. So one more, let's look at sulfur dioxide. Sulfur dioxide is SO2. Sulfur is in group 6. Oxygen is also in group 6. Times 2 is 12. So I have 18 electrons to distribute. So if I have 18 electrons to distribute, I'm going to end up needing 1 double bond. 2, 4, 6, 8. So this is the Lewis structure for sulfur dioxide. Except we see this unequal representation of this double bond, which means this has a resonance structure. So both of these are the Lewis structures for sulfur dioxide. Here's one with a resonance structure. So it doesn't matter what one you use because the answer will be the same. The steric number here, whoops, I forgot the lone pair there. The steric number is 3 because remember this double bond counts as 1 region. 1, 2, 3 regions of electrons. This has a steric number of 3. Even though this is a double bond, it counts as 1 region. 1, 2, 3. So the electron pair geometry for something with 3 regions is called trigonal planar. And the molecular geometry for something with 3 regions of electrons where 2 regions are bonds and 1 region is a lone pair is called bent. has the same name as water, where we had 4 regions of electrons and 2 with lone pairs and 2 with bonds. So the way that I would draw this is it would look like this. And you would not necessarily need to show the electrons on any of them. But this double bond could exist in either place. So these are some examples of determining molecular geometry from the shape of the Lewis structure based on how many things are connected to that central atom.